You got that it's a minor arc. Perfect for the first one. So let's put minor here. Okay. And then how many degrees did you get? Hey, excellent. How did you get 55 degrees? Yeah, 360 minus everything, or you could have done 180 minus 60 minus 65. However you want to get there, okay? But all you have to do is take 360, which is the measure of the entire circle, and then you subtract each one. Minus 60 minus 120 minus 60 minus 65. And you should get 55 degrees, okay? Or you could have done it like maybe separate this into two semicircles. You do 180 minus 65 minus 60, right? And then you would also get 55. Doesn't matter which way you go about it, but it should have been a minor arc and it should have been 55 degrees, okay? JLM. Samantha. It's a semicircle? All right, well, let's follow it around. Let's start at J. And then let's follow it around to L. Remember, we have to go in order of the letters. So here's L, J, L, and then finally let's go to M.
Oh, major.
It's a major, good. Why?
Because it's more than 180.
Yeah, very good. It's more than 180. And exactly how many degrees is it? Well, J to L is how many? 180. And then you're adding, how much is L to M? 65. So 180 plus 65, you should have gotten 245. Right? Okay. NLK. Marcos.
NLK.
Yeah, very good. And how many degrees are all semicircles? Excellent. 180 degrees. And Noah, you're up. LMN. Good. It's a minor. And how many degrees?
120.
Why?
Because
How do we get 120?
we added 60 and 60 and 120 from NJL, and then we subtract that from 360.
What?
Oh.
You just add, we already knew that this one was 55 from the first question. So you could just add the 55 and this and the 65.
Okay.
And then you get 120. So it would have been, whoops. So it's 65 plus 55. You see that, Marcos? Okay. All right, any questions on the warm-up? Okay, are there any questions from last night's homework? Going once. Going twice. Okay, perfect. All right, guys. Yeah. Mm-hmm. Okay, this is chapter 10, section 3. This is the last section that will be on your quiz on Friday, okay? All right, this section is all about chords. There's about 4 theorems that we're going to learn, okay? But guys, honestly, all the theorems are kind of similar. So if you understand the big picture, you're going to understand all of the theorems. The first theorem is the congruent corresponding chords theorem. In the same circle, or in congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. What that means, guys, take a look at this example, okay? It's telling us that AB is the same length as CD. Okay? That means the length of this chord, let me write in a better color. the length of this chord right here is the same as of this arc is the same as the length of that arc over there. The length of AB arc is the same as the length of CD arc. So if this was, I don't know, 100 degrees, this would also have to be 100 degrees. Okay, the second theorem is the perpendicular chord bisector theorem. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc, okay? What this means is take a diameter or radius, right? If that diameter or radius is perpendicular to any chord, it cuts it in half, okay? So take a look at our example. I want you to take a look, oops, take that out. Let's do this. At EG, okay? As a radius, if that cuts a chord, or if that intersects a chord at a 90-degree angle, then the assumption that we can make is that FH is the same length as HD. It cuts it in half, okay? Not only are those two lengths the same, but the two arcs that they intersect are also congruent, okay? So add congruence marks to both the arcs and to those two segments on either side of the chord. And just so we completely understand, okay, let's draw our own figure. So draw a circle. That's honestly one of my best circles. You guys can hold it down because you're in Notability, and it'll just make it a perfect circle for you. Draw a center. And then draw a radius. Don't draw it as a diameter. I just want you guys to see that it's the same for a radius, okay? Then draw a chord that looks to be at a 90-degree angle with that radius, okay? And then fill in the 90-degree mark. What happens is the length of this is congruent to the length of this, and these two arcs become congruent as well, okay? You'll see both examples. You'll see that blue line be a diameter, and you'll also be a radius. But all you really care about is the fact that there's a 90-degree mark right here. Then you can make all those assumptions. And this theorem actually works in reverse as well, okay? So there is a converse. The converse says that if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So notice how we don't know where our center is, right? In this diagram. But we know that SQ is perpendicular and it splits that chord TR in half. Then we know our center must be somewhere on this line because SQ has to be the diameter, okay? This also works in reverse. In this theorem, I want you guys to underline perpendicular bisector and that we are concluding that it's a diameter, okay? Our conclusion is now that it's a diameter. We aren't given the center. We're not told that it's a diameter. We are proving that it's a diameter. That's the definition of the converse theorem. The equidistant chords theorem, okay? In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center, okay? What that means is, remember when we're finding the shortest distance, okay? we always draw a perpendicular line to whatever line we're trying to find, okay? So notice how from each of the chords, there should be a perpendicular mark going back to the center, okay? That means that this is the shortest distance to go from CD, the line, the chord, to our center. Same thing here. To go from AB to the center, the shortest route is from F to E because it makes a 90-degree angle, okay? And what this theorem is saying is that if these two chords are the same distance, if FE is equal to EG, then our chords are the same length. AB and CD are the same length. And this one is an if and only if, so it works in both directions, okay? So if EF and EG are the same length, then we know that the chords are the same. And if the chords are the same, then we know that FE and EG are the same as well. Okay, one more thing on this slide. Let's say we extended both of these out to the edge of the circle. Are there other sets of congruent segments here? Think about the last two theorems we just talked about. Are there other sets of congruent segments here?
F and G.
F and G. Ah. Yeah, but we talked about that. That's the distance from the chord to the center. Think about CG. Is there going to be a segment that's congruent to CG? Yes, GD. And the same thing down here. For AF, it's going to be congruent to FB, okay? Because we just extended that line to make those distances from the chord to the center, we now just made them radius, right? We made it a radius. And when a radius is perpendicular to a chord, it's a bisector of it. So it creates two equal parts on both sides of the chord, okay? All right. Enough talking, let's do some examples. Okay. So in these examples, we're going to find the value of x and y, okay? So in our first example, we've got a diameter, which should be going through the middle. I think when it copied to Google Slides, it kind of shifted everything around, okay? But that should be going through the middle. We can consider that a diameter, okay? And it's telling us that this length of this length is 13 from here to here. It's telling us that this length is 5. And we're trying to figure out what y and x are. Okay, the first thing that I want you guys to notice is what's the relationship between y and x? Ah, I heard they're bisected. So what does that tell me about y and x?
Have the same measure.
Very good. They're going to have the same measure. Y is going to be equal to x. Now, why are they going to be the same measure? What in this diagram is so crucial that tells me that y is equal to x? There's one thing in particular.
90-degree angle.
Yes.
The 90-degree angle.
Excellent. If you thought about the 90-degree angle, you are 100% right. Because this diameter bisects the chord at a 90-degree angle, it splits it into two parts, okay? If it didn't have that 90 degrees there, we wouldn't know anything about x and y, okay? But now we know that they're equal because it's a perpendicular bisector. So perpendicular bisector. okay? So, but we cannot figure out x without figuring out what this side over here is. Does anyone have an idea of what that could be? It's not 8.
13.
Why is it 13?
It's another radius.
Ah, very good. It's another radius. This is our radius, and it's equal to 13, okay? Because notice, anytime you go from the middle of the circle to the edge of the circle, that is going to be a radius. It will be the same for the entire circle, okay? So this has to be 13. So knowing that this side is 13, how can we solve for x?
Pythagorean theorem.
Beautiful. Nice job, Teresa. The Pythagorean theorem. So someone set the Pythagorean theorem up for me for this to solve for x.
x2 plus 5.
5 squared plus x squared equals 13 squared.
Excellent. Why is 13 squared by itself? Because it's the hypotenuse. Excellent. Because it's the hypotenuse. Perfect. Okay, then we just solve this, okay? We know what 5 squared is. If we don't know what 13 squared is, you can always plug it into your calculator. You'll get x squared plus 25 equals, I think it's 169. Let me double check. Yes, 169. You can subtract 25 from both sides, and you're going to get x squared equals 144. You take the square root of both sides, and you get x equals 12. So we basically did two things here, guys. What we had to recognize was that x and y are the same. And the reason we did that was because of that 90-degree angle, okay? The second thing you needed to do was recognize, okay, that 13 down below is a radius. So then my hypotenuse of that small triangle on the left, the hypotenuse has to be 13 as well. So two assumptions you need to make. Once we find x, we know that x equals y, so y must also be equal to 12. Okay? Questions on this first one? Okay? So let's start with trying to find x. So, let's see. Well, we know that this is 6, this is x, and this is y. So we only technically have one of the sides of our triangle. But what else do we know about this picture?
It's at 30, 60, 90.
How do you know that, Juliana?
Because it says that one of the other angles is 60.
Excellent. That was a great observation. So since this one's 60 degrees, this one has to be 30 degrees, right? So let's just write down, we've got a 30, 60, 90, where the side opposite the 90 should be 2a, and what is the side opposite the 90 equal to? Yeah, it's just 6. So if we wanted to solve for a, we would get a equals 3, because we're dividing by 2. So now the 60 side should be the square root of 3 times a, and then the 30 side is just a. So the 30 side is going to be 3, and this 60 side will be 3 times the square root of 3. So let's fill that in. So the side opposite the 30 is going to be 3. And the side opposite this 60 is going to be 3 times the square root of 3. So we found x and y. So for this part of the problem, guys, it wasn't a circle problem at all, okay? It was a 30, 60, 90 triangle. But if we want to find the measure of arc AB, then it becomes a circle problem, okay? So, this is 3 times the square root of 3, so x equals 3 root 3, y equals 3. We need to find the measure of the arc AB. Now, how we find that, well, first of all, it should be whatever let's call this point C, AC is times 2, because it's going to be the same length on both sides of that arc, right? Because it's a perpendicular bisector, it's cutting not only this chord AB in half, but it's cutting our arc in half as well, okay? Does anyone notice what the arc AC has to be?
30.
It's not 30, you're close. What was that, Noah? 41? 45? No. Nope. Remember, the measure of an arc is equal to the measure of the angle inside, the central angle. So it should be what? 60. So if that's 60, then the measure of arc AB should be what? 120. Okay? Because it's going to be CB, the measure of the other side is just going to be the same. So this one's 60, this one has to be 60. Therefore, together they equal 120. Okay. Last one in this example, C, okay? So this is actually a poorly drawn diagram, or it came out bad. So I would like you guys to redraw the circle, okay? So redraw it over here on the right side. And then we're gonna put Y, which is from there to there. And then this one's like here to here. Here's the center. Okay, and it tells us that these two lengths from the middle to each chord is the same length, okay? And it's the shortest distance to the chord because of that 90 degrees. So if those two are the same, we know that these two chords are the same length, okay? We also know that each side of the chord cut by that line segment is going to be the same length as well. So what should be the value of x? What do you guys think? 8. And what should be the value of y? 16. Okay? So just remember, this segment's going to be equal to this segment, which is equal to this one, which is equal to this one. So this one's just 8 plus 8, which is 16. Now, the reason this works is because of these two pieces of information. It told us that the distance from the center to each chord is the same, and that it was being cut at a 90-degree angle, okay? If we didn't have either one of those, or we were missing one piece of information, then we wouldn't be able to say this, okay? We would not be able to conclude this. Okay, next example. Find the measure of the arc CD in the diagram. All right. Any ideas? What should we do? Well, in order to find CD, we need to solve for x. How are we going to solve for x, peeps?
9x equals
9x equals 80 minus x. Why are we able to say that, people?
because it's like those angles are equal.
Okay, why are they equal? I agree, both of those arcs should be equal. The arc CD is equal to the arc DE. But why, peeps? We need to know why.
Because of the 90 degrees angle.
Because of the 90. Okay, what does that tell us, though? What do we know about BD? What's special about BD?
It's 180 degrees.
It's 180 degrees, but what's special about the line segment BD? What is BD? It's the diameter. How is it? Why is it the diameter, KL? No. Yes. Goes through the middle, and what else? It goes from one end of the circle to the other. Okay, that's the definition of the diameter. So since BD is the diameter and it cuts that chord at a 90-degree angle, it bisects it. So it cuts these two into the same piece and these two into the same piece. Okay, that is super important. That was the first theorem we learned about. Okay, so because of that, then we can set them equal to each other. Okay, if we didn't know that it was 90 degrees, we wouldn't be able to say this. Okay. We set these two equal to each other, we just solve. So we add x to both sides. We get 10x equals 80, and then we divide by 10. X equals 8. Now, we found what x is, but how do we find CD? Yep, just plug it in. So we plug it into, you can plug it into 80 minus x, or you can plug it into 9x. Remember, but we're finding CD. They're the same, so it wouldn't matter. So the measure of CD, 9 times 8. (72 degrees). Okay, one more example, Pete. QR equals ST, which is 16. Find CU. QR equals ST, find CU. Now, this is the theorem that we learned, but in reverse, okay? So now we know that the two chords are the same length. If they're the same length, what should be true about their distance to the center?
They're the same length.
Very good. These two need to be the same length. So what equation can we set up to solve?
5x minus 9 equals 2x.
Excellent. 5x minus 9 equals 2x. Okay? But you have to recognize it's because the chords are the same length. If this one was 16 and this one was 15, you wouldn't be able to apply this theorem. Okay? Only chords of the same length are the same distance from the middle, or from the center. Okay, now we just solve this. Someone help me solve it. What should I do?
Subtract 2x from both sides.
We can subtract 2x from both sides. That's a good idea. What am I going to get on the left? 3x minus 9. And on the right? X. What's 2x minus 2x? It's just 0. Now what do we do? Add 9. So 3x equals 9, because these are going to cancel. And my last step, guys? Divide by what? Why? Why do I divide by 3?
To leave the x on its own.
Very good. We want the x by itself. And that's 3 times. Actually, you have to use the opposite operation. Divide by 3, and we get x equals 9 divided by 3 is just trace. So x equals 3. But take a look at what it was asking. How do we find CU?
2 times 3.
You just take 2x, you plug in x equals 3. CU equals 2 times 3, which is 6.